All right, so welcome. We're now in lecture 4, and this lecture is 1D Kinematics Part 2. So you would have already seen the lecture 3, which is 1D Kinematics Part 1, where we go over some of the basic kinematic equations and how to use them in problems. But today we're going to be doing Part 2, where the questions just get a little bit more challenging. Okay, so we're going to look at acceleration due to gravity. So this is just one thing that if the question doesn't tell you what the acceleration is, but you know that gravity is the only force that's acting on the object, then we already know what the acceleration due to gravity will be. And so that's just going to be another value that we know that's not going to be explicitly told to you in a question. We're also going to learn how to deal with inclined planes. So how to do kinematic problems when we have inclined planes. And we also are going to deal with questions that have multiple accelerations. So maybe for one part of the question, it's accelerating, the object's accelerating at a certain rate, and then later on the acceleration changes. And so we'll look at how to deal with that. And then finally, a common question that you're going to see is one object catching up to another. So you have two objects. They both have different accelerations and velocities, for example, but one will catch up to the other. Okay, so I see that there's a question right now. Does anybody want to turn on their microphone to ask the question?
Hi, I did want to make a comment. It's off topic, though, if that's okay.
That's okay.
So there is, in fact, a laboratory for intro to engineering from like right after your lecture on Friday.
Oh,
and
okay. So
it encompasses your entire time period for the lecture if you postpone it. So
can you say that again?
It would encompass most of your lecture if you do choose to postpone
Right,
it
because
on
it's from
Friday.
5:30 till 7, right? And you're saying from 3:40 till 6:30.
Yeah.
And are you there for the entire lab?
Yeah, unfortunately, the person who, that's why we had to leave your class last week as well, because the person seems to be very specific about punctuality and his time.
Right.
And
So can I ask, like, do you want me to put another options for it to start at 6:30 and go till 8? Do you want that to
I would be more than happy to do that, actually. I'm not sure.
I'll put that on this survey if people don't mind. I'm sorry that I'm changing this, but I totally understand, and I'm happy to change, like, to accommodate as much as I can. And I know it's like it's my fault, right? Like the reason that this is happening is because of me. So I'm like very happy to accommodate as much as I can. So I'm going to put an option in as Fridays from 6:30. I'll say 6:40 till 8. Friday night together. So I'll put that in. Anybody who wants to, if that is a time that would work for you, please just click on that link again. It's not ready yet. I think it should be there now. Can somebody check it? Can you see that as an option now?
Sorry to just make this a little bit more messy, but it is until 6:40. That was a typo. I'm so sorry. So, I mean, we can definitely try to run to your class as fast as possible. If you could
just wait, it's an online class, right?
Oh, good point. Okay, fair enough. So you're not doing anything in person?
Not for lectures. No, lectures are always online.
Fair enough. Okay, thank you.
Okay, so I already have some people that have said 6:40 till 8 work for them. So if other people who chose 5:30 till 7, 5:30 to 7 right now is in the lead. So if other people are okay with 6:40 till 8, you can select that option as well. Okay. And as I mentioned earlier, if you do end up coming late to class, that's completely fine. It's not a disruption at all. And if you have to leave early from class, that's totally fine. And then you would just review the lecture note or the lecture video after the fact. Okay, I know it's not ideal. This isn't a perfect situation, but hopefully there's enough people that will be able to still attend. Okay, so continue to complete those surveys. I see 10 people have already gone in and made some changes. So go ahead and do that. And I'll let you know by the end of this lecture what that looks like.
Professor, I've actually filled the survey twice already, and the point that Kunal raised, I have the same problem. Like, I have a lab till 6:30.
Yeah.
So that's why I asked you earlier that if I could join 30 minutes late.
Yeah, I know.
now that another time slot opened up, so should I fill in like the survey for the third time as well?
Yeah, go ahead. If you haven't picked 6:30, pick that one, because if there's a lot of people that are able to attend, then that will work as well.
Okay,
then we
thank
can
you.
do that, okay? 6:30. So right now, I haven't changed the lecture time. I'm waiting for people to complete the survey. By the end of this lecture, I'll let you know which time we're going to select. Okay? All right. And like I mentioned, it's going to be recorded, so you could still view it. And you can always contact me, and I'll meet you one-on-one if you need it, okay? And the change comes into effect after today. So this is the last lecture during this time. Okay, so let's move on to this topic. The first topic is now acceleration due to gravity. So if an object is thrown straight up or straight down near the surface of the Earth, then it's going to accelerate at a constant rate. What is that rate? What's the number?
9.81.
Yeah, good. So it's 9.81 meters per second squared. Sometimes, like some textbooks, they use 9.8. Sometimes they use 9.81. It doesn't matter so much, except on your test, there's a formula that I'm using to calculate people's correct answer. And in the formula, if this is used, I'm using 9.81. It says so at the top of every test in the introduction. It will say, like right above where the formula sheet is, that use acceleration due to gravity equals 9.81 meters per second squared. So just use that instead of 9.8 when you're doing your tests. And that's it. I'm just looking at some people's responses. We can interchange lectures from asynchronous to synchronous. I'm not really sure what you mean by that. Anas, did you want
in a group, it is we can change the Wednesday lecture to the synchronous one, the live lectures, and Friday to the weekly test.
Oh, yeah, no, I'm not going to be able to change that. I'm going to keep the Wednesday one the same, but the Friday one is the only one. The synchronous will just change a different time. But that, I understand the suggestion, but it won't work. Okay, thank you. All right, so I'm going to put in 9.81 meters per second squared. All right, so let's do some of these questions here. So as I was mentioning, when you know that the object is the only force acting on it is gravity, the force of gravity, then the question will not tell you what the acceleration is. You just need to assume that it's 9.81 meters per second squared. Now, what happens if the object is thrown up into the air and it's on its way up? What is the acceleration?
Negative 9.81.
Okay, good. So positive and negative just depends on which way you want to define positive to be. If we say that positive direction is up, then the acceleration due to gravity is negative 9.81 meters per second squared. What happens when it's at the top of its peak? So it's right here. What's the acceleration due to gravity right then?
0.
Okay, I see some answers are coming in. And it's a very, very common answer, but it's a misconception.
The speed is 0. The acceleration still remains.
Yeah. So at the very top, the velocity is 0. But the acceleration is still 9.81 meters per second squared. And which way is the acceleration pointing?
It's always downwards.
Yeah, it always points down. So if we say up is positive, then the acceleration is negative. If we wanted to say down was positive, then the acceleration would be positive. Okay, so at the very top, the acceleration is still negative 9.81 meters per second squared. What happens when the object is on its way down? What's the acceleration?
Still constant, 9.8.
Yeah, it's still negative 9.81 meters per second squared. It's still pointing down. Okay, whether it's on its way up, whether it's at its peak, or whether it's on its way down, the acceleration is still the same number. It doesn't change. It's the velocity that changes. On the way up, if you say up is positive, then on the way up, the velocity is positive. At the maximum point, the velocity is 0, and on its way down, the velocity is negative, right? But the acceleration doesn't change. Think of acceleration. Remember when we talked about, we're going to talk about Newton's second law, F net equals ma. If we were talking about net force acting on an object, if you're throwing an object into the air and it's already left your hand, now it's just in free fall. It's either on its way up, it's at the max, or it's on its way down. Either way, the only force acting on that object is the force of gravity, and the force of gravity points straight down. Whichever direction the force points, that's the direction the acceleration points. It doesn't change. It doesn't matter where it is in its path. The acceleration is always the same number. Okay, so that's important to know here. It doesn't change. So we're using 9.81 meters per second squared down, no matter where you are in your path if you're in free fall. Any questions about that? So let's write out for question 1, what is all the information that we know? So the observation deck of a tall skyscraper is 370 meters above the street. So let's say it's here. And this is our height. So I can call it height. I could call it y since it's a y direction, or I could call it s. It doesn't really matter, s being generic. So it could be x or y. And this is my time. So I throw it up into the air. Determine the time required for a penny. Oh, sorry, don't throw it up. The penny is just in free fall, and it's going from the deck to the street below, assuming that it started from rest. So that means it starts from rest over here, and it just kind of falls down to the ground. Okay, so it kind of looks like this. And it lands on the ground, and we want to know how much time has gone by for it to land on the ground. So what is the information that we know? So what is the distance or the displacement traveled by this penny? So before we start, we need to decide which way do we want the positive direction to be. And this is something that's up to you. So a lot of times people want to say up is always positive, down is always negative. Yes, I'll zoom in. Sorry, I didn't see your question. Okay, a lot of times people want to say up is always positive and down is always negative. But it always depends on the person doing the work. You can decide which way you want positive and negative to be. Okay, it's completely up to you. So for example, in this case, the way I like to do it is I like to say the direction that the object is moving is the positive direction. In this case, the object is moving downwards. So that's the way I'm going to say it's positive. And all you have to do is write a plus and an arrow down to tell me that's the direction you're assuming is positive. And as long as you stick with that the whole way through the question, then you're good. And somebody else might do the same question with up being positive, and then you still get the same answer at the very end. So if down is positive, then what would we say as being our delta S? So what is the change in position of our object from where it began when it was at a height of 370 meters to where it ends up on the ground? What is that change in height if down is positive? Yeah, Pardis already answered. Yeah, Marion, good. Okay, if down is positive, then the change in the height would be 370 meters. It's confusing for people though. If up was positive, delta S would be negative 370 meters. Right? Because you went down, you started off at a height of 370, you ended up on the ground, so your height went down. And if down is negative, then your delta S would be negative. So we can think of this question in two ways, depending on what makes more sense to you. You can choose which method you like better. It's just about which way do you want to define positive direction to be. Okay, so if down is positive, delta S is 370. We want to know what is the time required. So it's our delta T is what we're looking for. So I'm doing this question twice. You just pay attention to the side that makes more sense to you. We want the penny to free fall from the deck to the street below. Since we're in free fall, what is our acceleration? If down is positive, what would we say our acceleration is? Yeah, 9.81. What if up was positive? What would our acceleration be? Good. Okay. Assuming it started from rest. So starting from rest, what does that tell us about the question? Our initial velocity, good, is 0. Does it matter if we're up is positive or down is positive? Does it make a difference? No difference, because positive 0, negative 0, there's no difference, right? Because it's just 0. Good. So we have everything that we need to know here, and we can solve for this question, and we can solve it both assuming down is positive or up is positive. It really doesn't matter. So let's start with down being positive. So we're looking for delta t. We don't know anything about v final, and we don't want to know anything about v final. So v final in both cases, whether up or down is positive, is the one variable that we don't care about, we don't know, and we don't want to know. So we're looking to use the kinematic equation that does not involve v final in it. Okay, so we have 3 kinematic equations, and the one that does not involve v final is the one that looks like this. S final equals S initial plus v initial delta t plus 1/2 a delta t squared. Okay, so instead of having S final and S initial, we have delta S, which just means you need to take your S initial to the other side so that you get S final minus S initial, and S final minus S initial is the same as delta S. So these two equations are the same thing, but on the formula sheet, you get the one above, right? We get this equation. You just need to know how to bring the SI to the other side and turn SF minus SI into delta S. Anybody have questions about that? Okay, so now we can start to plug in the things that we know. We're trying to solve for delta t, which means we can't isolate it for it first in our equation, because it looks like we might have to end up using quadratic formula depending on whether or not any of these terms are going to cancel out. So let's just plug in the numbers we know. Delta S is 370. V initial is 0. So that's nice. This whole term goes away because it becomes 0. 1/2. My A is 9.81. And then delta t squared. Or I can do it when up is positive. My V initial is still 0, so that term goes away. And I get negative 370 equals 1/2 negative 9.81 delta t squared. Can you see already that the delta t will be the exact same number, because this negative here and this negative here will end up canceling out. So it won't make a difference. So my two equations are exactly the same in the end. Okay. Okay, Matthew, good. I'm glad you can see it. And thanks, Ali, for explaining it. Okay, so now we just have to solve for this. So we have 370 divided by 1/2 times 9.81 is my delta t squared. Okay. And then I can just plug that in. Does anybody want to type that up? Delta t squared equals, and I can do that on the other side as well. Okay, so delta t itself, I think, is the 8.69. What are we getting for delta t squared? Good. 75.433. And then we just need to get rid of the squared. So we square root 75.433 and we get 8.69. So it doesn't matter whether up was positive or down was positive. Mohammed, do you have a question?
Yeah, so I understood this whole process. The only thing that I missed was at what point, like, how could we just cross out the delta t?
Oh, okay. It's because the question tells us the initial velocity is 0.
Okay.
And so if we plug in a 0 for this initial velocity, 0 times anything is 0. So then it just goes away.
Oh, got you. Okay,
that's all we did. I just didn't bother writing it down in the equation as a 0. I just canceled it out. Mohammed, do you have a question?
Wait, sorry.
Yeah, I have. Yeah, go on.
Sorry. Your names are, I'm pronouncing them the same, so it's confusing.
My question is quick, but I just wanted to say, in reality, the delta t isn't 0. We just know mathematically it will be canceled out because the vi
That's right.
is 0.
It's not the delta t that's 0. It's the v initial that's 0, and 0 times it goes away, right?
So it just doesn't matter. But okay,
yeah.
I got it. Thank you so much.
You're welcome. Okay, Mohammed?
Yeah, I had a question about acceleration. Do we have to put squared if it's negative?
Oh, this has to be.
You didn't put it on the left side.
Yeah, that was a mistake.
Oh,
thanks for correcting me.
okay.
That should be squared.
Sorry about that.
Yep. So the units are always meters per second squared, unless it's something like kilometers per hour squared or something, and then you'd have to convert the units. Okay, Matthew, do you have a question?
Yeah, I was just wondering, the 370 over there, like, because oh wait, never mind. How did you switch the 370 with delta t squared on the just on the left side at like the fourth last line?
Yeah. So over here.
Yeah. Around there. Yeah.
So all I did was I replaced delta s with 370 because 370 is my delta s, right?
Oh, I see.
And then I rearranged the equation to solve for delta t squared.
Oh, okay. So that's why you end up dividing. Okay, I see it now.
See it? I
Yeah,
rearranged the equation to find the delta t squared and then square rooted it to get delta t.
Yeah.
Avinash, do you have a question?
Yeah, is it supposed to be 4 significant digits?
Okay, so in this question, you're right. There should be 4 significant digits. So I know in the labs that they want you to be careful with significant digits. In the class, like on tests, because we're using Canvas, Canvas is not able to discern between, I'm not able to tell Canvas how many significant digits the answer should be accepting. So that's why in Canvas, I tell you to answer it leaving this many number of significant digits. So you're right. We should really be leaving an extra digit here. If somebody wants to give me one more digit, the 8.69, if there's something after that, then we can put that in. But on a test, I don't want you to worry too much about it. It will tell you on the question, answer everything with 2 decimal places unless stated otherwise, and it will tell you in the question. Okay? Yeah, and the S is seconds, not a 5. Okay, so yeah, there's a 0 at the end, I guess. All right. Any other questions about number 1? I just want to highlight, because I know people get very confused about positive directions, which way you want it to be. So just make sure if you're thinking that down, you want to make down positive direction. The object started at 370, ended up at the ground. So the delta S, the change in the height, is 370 if down is positive. But if up is positive, then since it traveled downwards, then you've got a negative delta S. Okay, I hope that's clear. So let's do question 2. Oh, sorry. Let me make the change with the number here. So 8.685 seconds. And that's because in the question, there were 4 significant figures. So in our answer, we're putting 4. As I said on the test, I'm not being picky about it. I'm telling you how many decimal places to leave. Okay, Mohammed, do you have a question?
Yeah. Wasn't the 370 supposed to be on the bottom? Like, I don't get how it's on the top.
Okay, let me do it on the side here. So I have 370 equals 1/2 times 9.81 delta t squared. So I'm trying to solve for delta t squared, right? First, eventually I just want delta t. So that means I want to get rid of the 1/2 and the 9.81 so that it will cancel out. And so now I have delta t squared is equal to 370 divided by 1/2 times 9.81. Do you see why it should be on top?
Yeah, you just did it the other way. I thought you did 370 divided by 370.
Yeah. No, you want delta t squared by itself, so that means you need to get rid of the 1/2 times 9.81.
Okay, all right, thank you.
Yep. So if you had something like 3x equals 9, you're dividing both sides by 3 so that the x would be by itself. Right? So that's the same idea. It's just more complicated with these numbers.
Okay, thank you.
Yep. So number 2, a stone is dropped into a deep well and is heard to hit the water 3.41 seconds after being dropped. Okay, Kunal, do you have a question?
Hi, sorry to bother you, but
No, it's okay.
so gravity is 9.81, right? That's the given number.
That's the acceleration. Yep.
Right. So it's given to 3 significant digits, right?
Yeah.
So the final answer should be in 3 significant digits because it's the limiting factor of the equation.
Yeah, you're right.
Right?
Yep. So the
question
question did include this acceleration is 9.81. You're right. Even though it's not written in the question, we should still round to that amount. Thank you. So I'm going to go back to the original. Again, as I was saying, in the test, this is not something you need to worry too much about because I tell you how many decimal places. But on the lab, it is something that in labs, it is something that they want you to look at. So thank you for clarifying that. Okay, so the stone is dropped into a deep well, heard to hit the water 3.4 seconds after being dropped. Determine the depth of the well. So let's just write out all the information that we know. So what is it that we know here? So what's the given? Time. So by time, this is the amount of time it took for the stone to hit the ground. So this is the delta T. Is 3.41 seconds. Okay, what else do we know? There's some things here. Yeah, okay. So there's some things here that there's no other numbers given to you, really, right? So it looks like there's only one known, but there's actually more. So it's delta T because it's the amount of time that went by for the stone to hit the ground. It's not the initial time and it's not the final time. It's the amount of time that went by. So that's delta T. That's what delta T means. It's the change in time. So it might have started off, let's say you start the timer at 5 o'clock and now it's 5:03. Then that means that 3 minutes went by. So 3 minutes is your delta T. Okay, so what else is it that we know? S initial is 0. So that's up to you. Wherever you want S initial to be, we can say, let's say this is the bottom of the well here. And the stone starts up here and it drops and it lands on the bottom somewhere. Okay, it hits the water 3.41 seconds after being dropped. Determine the depth of the well. So it's up to you of where you want to say your initial position is. If you want to say this starts off at 0, and then in the end, whatever your number is that you get, that would be your final position. You can do that. Or you could say, I want to know what my delta S is. That would be the change in position from the initial to the end. Okay, so the initial position, or somebody had mentioned, Daniel, you mentioned the final position is 0. So we could say that this position over here at the end is 0, and this initial position is what we're looking for, because we want to know how deep the well is. So this is probably, to me, the one that makes the most sense. There's no negatives involved, so it's probably less confusing. And so that's completely up to you of how you want to design the question or how you want to draw it. But I'm going to stick with this setup. So my initial position, my initial height, that's what we're looking for. We want to know how deep the well is. So I'm looking for that. And I'm going to say that when it hits the bottom of the well, that height is 0. Okay. Somebody else mentioned V final is 0. And somebody else said V initial is 0. And somebody's talking about the speed of sound. Okay. So the speed of sound in this question, you're right. This question is making an assumption that the speed of sound is so fast that when you hear that the stone hits the bottom of the well, it's immediately after it hits the well, it hits the bottom. So as soon as the stone hits the bottom of the well, we're assuming we heard it right away. So this 3.41 seconds, we're saying that's how long it takes for the stone to hit the bottom of the well. We're not taking into account the fact that the sound waves still have to travel to our ear for us to hear it. So you're right, that question could have been clarified a little bit better. We're going to assume that that 3.41 seconds is how long it took for the stone to hit the ground. Okay, so we're ignoring the speed of sound, which is how long it would take for the sound waves to then travel to our ears. Okay, we have a V final and a V initial. 2 people suggested that those are both 0. One of those is 0. One of them is not 0. Which one is 0?
So I think V initial is 0 because they have said that you drop the stone.
Yeah.
Right. So
the
that
word
means there's no
drop.
acceleration aiding the falling of the stone. We usually calculate right before it hits the surface to make the velocity 0. So it's not necessarily 0.
Yeah, exactly. Okay, so that is something that I was trying to mention before as a very common misconception. People think that if you drop something onto the ground, so you drop a stone and it hits on the ground, they say, okay, the final velocity of that stone as it's hitting the ground is 0, because after it hits the ground, it stops and then it sits there. So of course its velocity is 0. But when we talk about final velocity, we don't mean after it hits the ground and now it's sitting there on the ground resting and it's not moving anymore. When we talk about final velocity of an object that falls and hits the ground, we mean while it's hitting the ground, as it's impacting the ground, what's the velocity? So it's clearly not 0, right? Because it's coming down faster and faster. It keeps getting faster and faster, and then it hits the ground. It's that velocity as it's hitting is the final velocity. That's not 0. We don't know what that velocity is. We could calculate it, but the question doesn't tell us and it doesn't ask us for it. Okay, so the final velocity in this question is not 0. Does that make sense? Okay. So V initial 0 because of the word dropped in the question. A stone is dropped. If it wasn't dropped, if it was thrown, it would have had to tell you what velocity it was thrown at. So then that number would be given to you. But when it says dropped, we automatically know that the V initial is 0. That's what that implies. Okay. The other thing that's implied is because we're dropping something into a well, we're assuming we're near the surface of the Earth. We're not on a different planet because it wasn't mentioned. That's something we're going to talk about at the very end of this course. But right now we're near the surface of the Earth where gravity is always the same value, 9.81 meters per second squared. And we just have to decide if we're making it positive or negative. And that all just depends on which way we wanted to say positive would be. So in this case, our final position was 0, and our initial position, the way we drew it, we're saying that our initial position is some positive number. So we're implying here that up is positive, right? Because our initial position is up high, and we want a positive value for our answer. And so we're going to get, we're basically saying that up is the positive direction for this question. Does that make sense to everybody? Yeah, so if up is a positive direction, then we need to put a little negative here in front of acceleration, because acceleration always points down. So if we say up is positive, then acceleration is negative. Why is up positive? Well, in this question, it's up to you to decide if up is positive. If you want down to be positive, then when you calculate your S initial, you're going to get a negative value. And that's fine because you said down was positive. So this is like you would be saying that this is your y-axis and up here would be your negative y-axis. So then you would end up with an S initial that's negative. And I think for a lot of people that's a bit confusing. So I chose to stick with the fact in this question that the up direction is the positive y direction. And so the initial position would end up being positive. And so in that case, then up would be positive. Okay, but again, just like question 1, you could decide to say down is positive. And if you do that, then you'll find SI, when you calculate it, it will end up being a negative number, which makes sense because down is positive and SI is up. So for this question, we're choosing up to end up with a positive answer, but you can do it as well if down was positive. Yeah, exactly. Okay, so that's what confuses a lot of people is whether you want to say up is positive or down is positive. Just pick a direction to be positive, whatever makes sense to you, and stick with it. Make sure it applies to everything. So we're saying up is positive, so acceleration is negative, because acceleration due to gravity always goes down. So now we're just solving for that SI in this question. So again, we don't know V final, and we don't want to know V final. It's not asked for us. So we're going to choose the equation again that does not include V final. So we're choosing this equation, S final equals S initial plus V initial delta T plus 1/2 A delta T squared. S final, we know. S initial is what we're looking for. So if we wanted to, at this point, we could rearrange the equation right now to solve for S initial. So we can bring everything else to the other side by changing the sign. So the pluses become minuses, and then we're left with S initial. Okay, you can rearrange the equation first and then plug everything in, or you could plug everything in first and then rearrange to solve for what you're looking for. It's up to you. So I'm going to just rewrite S initial on the left instead of on the right. My S final is 0 minus my V initial is 0. My delta T is 3.41 minus 1/2. My A is negative 9.81. My delta T is 3.41, and that's squared. Notice 0 times 3.41, that's just 0. So that's gone. That's nothing. And so now we're just typing this into our calculator. And I'm getting 57.04, and that's meters because it's a height. Okay, if we talk about significant figures, there's 3 figures here, and there's 3 in acceleration, so our answer should have 3. So I should round this to be 57.0 meters. Okay, but on a test, it will tell you to keep 2 decimal places. So you would put 2 decimal places, 0.4. Any questions about number 2? Okay. Okay, so we're going to move crystal clear. Does that mean, are you joking? Because they're so LOL. Do you have any questions, Mohammed? Okay, good. It's clear. Good. I can't tell if people are joking in a chat. All right, inclined planes. All right, so if an object is sliding up or down a ramp, so let's say we have a ramp over here, and we have an object on the ramp, and it's sliding up the ramp or down the ramp, okay? Acceleration is due to gravity still, right? Because gravity, we're going to assume in this case, there's no friction or anything. Gravity is still the force that's acting on the object that's making it move. So the acceleration is still due to gravity, but acceleration due to gravity points straight down. And the object is moving, let's, for example, say the object is moving down the ramp. So this is the direction of the velocity, okay? When you're using kinematic equations, everything has to be in the same direction. So you can't have acceleration pointing down while velocity is moving in this direction on this angle on the ramp itself. They can't be in different directions. They have to be on the same direction. Gravity components, good. So that's why we need to turn the acceleration due to gravity into different components. Now, if I do that, I'm going to just make this a bit bigger, maybe change the color. Okay, so this gravity over here, it always points straight down. So I'll call that G. Now, if I want to change the components of it, I want 2 components. One component which is parallel to the surface of the ramp, and that's the component that I care about when I'm using acceleration in my kinematic equation, because that acceleration, which is parallel to the ramp, is going in the same direction as my velocity, or opposite direction, but it's in the same component. So if I take that gravity and I want to decompose it into a vector that's parallel and then perpendicular to the ramp, I'll end up drawing a triangle where one of the sides of the triangle is parallel to the ramp, the other one's perpendicular, and the G, the force or the gravity, the 9.81 that I started off with, is the part of the triangle that's the hypotenuse. Okay, so anything you decompose or you break down into the 2 components, X and Y components, the thing you started off with is always your hypotenuse. So you would never do something like this, for example. That is not decomposing gravity vector, because now what did I do? I didn't keep my gravity vector as being the hypotenuse. And this vector over here, if I were to draw it as a vector with an arrow, is not parallel to the surface of my ramp. So that's not correct, okay? And that's a common misconception here, common error when people decompose a vector. I need a vector that's parallel and a vector that's perpendicular to the ramp. So perpendicular to the ramp would be like this. And parallel to the ramp would be like this. And you see that when I do that, my gravity vector, my initial vector, is my hypotenuse. And that's what's super important. It has to be your hypotenuse. So these two original vectors are perpendicular to each other, so they make the 90-degree angle. And opposite of that 90-degree angle is your hypotenuse, which is your original gravity vector, whatever vector it is that you decompose into x and y components. So before we move on, we really need to put arrows on these two vectors because right now they don't have any directions to them. So we have two vectors, and when you add them up, you need to get the vector you started off with, the g vector, gravity. So when I do that, I would get this that points downwards on this angle, and then this other vector pointing this way. And do we see how that when we add those two red vectors, we get the g vector? So this vector plus this vector gives us, well, let's draw this better, gives us this vector over here. Okay, so if we were to draw them going in different directions, for example, it wouldn't work out. It wouldn't be the g vector. So we need to draw the arrows on the vector so that when we add those two vectors, we get the original g vector, the one we decomposed. Any questions about that so far? So now we need to figure out how do we decompose these two vectors. First, we need to think about the angle that's here. So if this angle, we call it theta, we need to figure out where does that theta angle end up in the triangle that I just drew with the red vectors and the blue original g vector. So does it end up at the bottom over here, that theta, or does it end up at the top here? Because we know it definitely doesn't end up here because this is the 90-degree angle. So is it the bottom angle or is it the top angle that equals to the theta angle? The top, yeah. So let's prove that to ourselves. If we were to extend this to make a right angle triangle, this is 90 degrees. And then this angle over here, how would we calculate it? We know all the angles in the triangle add up to be what? 180. And we already have an angle down here that's 90. So that means that these two angles have to add up to be 90, right? Because 90 for those two plus the right angle, 90, all together would make 180. So if we know the bottom angle is theta, then this angle here would be 90 minus theta. And if that's 90 minus theta, then the one that's touching it, oops, the one that's touching it over here would have to be theta. So if we want, we can do this with actual numbers because it's a bit confusing. So let's say this is 30 degrees. Then the one on top would have to be 60 degrees because when we add all three angles, we get 30 plus 60, which is 90, plus the 90, which is 180. So that works out. And if that's 60 degrees, then the one that's touching it over here would have to be 30. So notice that this original angle is the same as this angle at the top of our new triangle that we drew. Okay, so that's what's really important here, is to recognize that the angle of your ramp is the same as the angle that's up here in the triangle. And if you know that, then you could decompose G like we did before. So if this arrow that goes straight down is G, then what about this side here, which is adjacent to the angle theta? Since it's adjacent, would we be using cos or would we use sine? Cos, good. So it would be G cos theta. And what about the one that's opposite of the theta degree? So this vector here, it's opposite. So should we use cos or sine? Yeah, good. So it would be G sine theta. Okay, so which of these two are we going to use when we're using our kinematics equation for acceleration? Are we going to be using the G cos theta or are we using G sine theta? Okay, G cos theta is perpendicular to the motion of the object, that acceleration there is not helping the object move down the ramp, right? It's not the component of acceleration that we care about when we're using kinematic equations. It's the g sine theta. That's the acceleration that's helping the object move down the ramp, right? It's making it accelerate down the ramp. Even if the object is moving up the ramp, so even if the velocity is going up the ramp, the acceleration is still going down the ramp, right? Because gravity pulls things down. It doesn't pull things up. Okay, so if the object is moving up the ramp, we could say up is positive, then the acceleration would be a negative value. And if the object is moving down the ramp, we could, if we wanted to say that positive is the down direction, and then acceleration would then be positive because it's going down the ramp. Okay, any questions about that? Because I know that's pretty confusing. So what would I put in this blank spot here? When an object is sliding up or down a ramp, the acceleration will equal the component of gravity parallel to the ramp or the plane. So the acceleration we're using in our kinematic equation is this one over here. And normally we say that the direction of the ramp is the x direction. Okay, so this would be like your x-axis, and this direction perpendicular to the ramp is the y direction. So this we could say is g in the y direction, and this is g in the x direction. Okay, and I'm using g, but I could have called this a instead. Acceleration due to gravity, still acceleration in the x or in the y direction. So these are my accelerations that I would use in my kinematics equations. Okay, but it's the ax is the one we care about because that's the one that's helping the object move down the ramp, or the acceleration that's making it harder for the object to move up the ramp. Okay, so let's do question 3 and see if this all makes sense when we put it all together. So a boy rides his skateboard 73.4 meters up a ramp. So he started here and now he's here. 73.4 meters is how far he traveled. At that point, the boy stops and coasts back down the ramp. Okay, so now the boy is going down the ramp this way. Okay, that's the direction he's moving. And the ramp is at a 10-degree angle. So that always means to the horizontal. How much time does it take for him to make it back to the bottom of the ramp? Okay, so what do we know in this question? So he started off here, he ends up here. So what does that tell us? What's that 73.4? Yeah, that's our delta S. Okay, if you wanted to, you could have also said, this is my initial position is 0, and my final position is 73.4. And that's the same thing as saying delta S is 73.4. So it doesn't matter which way you like to do it. But by doing what we just did, we just assumed that down the ramp is the positive direction, right? Because he's traveling down the ramp. And if we just said that it's positive, then that means down the ramp is positive. What else do we know in this question when it comes to the kinematic equation variables? Acceleration. Okay, so are we going to say that the acceleration is 9.81? Because which way does acceleration equal 9.81 point? It's gravity, so it's pointing down. But this boy on the skateboard is not traveling straight down. He's traveling on this ramp, on this angle, right? He's going this way. So we need to find the component of acceleration that's parallel to the ramp. We can't just use 9.81. We need to find the component that's parallel to the ramp. And if you look at the drawing that we did on the side, what would that equal? Yeah, so it would be sine of 10. So good. This sine of 10, because we're finding the x component of our acceleration. But now it's not, it should have a g in front and not the 73.4. So let's do that one again. the acceleration, the component of it that's parallel to the ramp, which we called AX, it should equal, good, G sine theta, and G is 9.81. So it's equal to 9.81 sine of our angle, 10 degrees. Okay, and then you need to decide, is it positive or negative? So we just said that down the ramp is positive. So if it's positive going down, then this acceleration would be positive. Dafari, do you have a question? Does anybody have a question that they want to ask right now? Yes, Matthew.
Could you just quickly go over the process of like solving these types of questions? Because I kind of
confused.
Need a refresher, yeah.
Yep, no problem. So what we're doing right now is we're just identifying whatever variables we know from the kinematic equations. So the first thing that we decided was that delta S is 73.4 because the boy is at the top of this hill, like 73 meters about like on the hill from the bottom. And now at this point, he's stopping and coasting down the hill. So from this point where he is to the end, he travels 73.4 meters. So that's our delta S. That's the change in position, how far he's traveled. And because we've said that delta S is positive, we're implying then that going down the hill is the positive direction. So that's the first thing that we know. The next thing is because the only force that's acting on the object, this boy on his skateboard, that's making him go down the hill is the force of gravity, then acceleration is just due to gravity. But because the object is not moving in the direction of gravity, so it's not just moving up and down, it's moving along the ramp, we need to find the component of the acceleration that's parallel to the ramp. So the component that's parallel to the direction he's actually moving. Okay, and that component is the component that's parallel to the ramp, which we called over here AX. And since it's opposite of the theta, the angle, it would be the acceleration due to gravity sine of theta. So it's 9.81 sine of theta. And in this question, theta, the angle of incline of the ramp, is 10 degrees. So far, we just know these two kinematic variables. We're saying acceleration is positive because we already said positive is down the ramp. But there's more variables that we know here. So we're going to keep putting them, like writing them down. And then once we have them all, we'll use a kinematic equation to solve for the missing variable. So what else is it that we know? What other piece of information do we know in this question? And it's from this word right here. What does that tell us? Yeah, the V initial is 0. So initially, right before the boy coasts down the hill, his velocity is 0. So we know delta S, we know acceleration, we know V initial, and we're looking for how much time does it take. So we're looking for delta T. That's our question mark. We don't need VF. That's right. The question doesn't ask for VF, so that's the one we don't know, we don't need to know, so we're going to use the equation that doesn't have it. Mohammed, do you have a question?
Yeah, so because I'm new to physics, the reason when I see the word stops, I'm thinking of it stops at the end. So then that's why I always think VF is 0, but you say VI. So how do I understand that stops means
you know
initial?
what? This question's a little confusing. So this is the story. The boy rides his skateboard up the hill, 73.4 meters.
Yes.
And then he stops. Yeah. And then he coasts back down the hill. So okay, the first part of the story is not relevant. He goes up the hill and then he comes to a stop. So that part, okay, fine. He's 73.4 meters up the hill and he stopped. Now pretend that this is now the beginning of the story. Now okay. He coasts down the hill. How long does it take for him to get to the bottom?
Okay, I get it now. Thank you.
Yep, no problem. Does anybody else have a question? Dafari, did I answer your question or are you confused about the acceleration in the x direction?
I wasn't asking a question. I was just that was me asking earlier when you were asking how to calculate the gravity, like the force gravity. And I was just putting in my answer.
Yeah, and that was all right. Perfect. Thank you. Okay, so now we have our kinematic equation. I chose the first one again because that's the one that doesn't have V final in it. Notice that I already brought my V initial to the other side. My S initial to the other side of the equal, making the equation delta S equals V initial delta T plus 1/2 A delta T squared. And we're solving for delta T, but our V initial is 0. So again, since V initial is 0, this whole term becomes 0 and it's gone. So we're left with just delta S equals 1/2 A delta T squared. And I can rearrange and solve for delta T now if I want, and then plug in all the numbers, or I can substitute in all the numbers now and then rearrange. I'm going to rearrange now. So I'm going to divide both sides by 1/2 A. So I get delta S over 1/2 A equals delta T squared. And I then get delta T equals the square root of all of that. I can bring this 1/2 to the top if I want as a 2. So dividing by a half, remember the division by a fraction is the same as timesing by the reciprocal. So I can bring that 2 to the top if I wanted to, okay? If you don't want to, you don't have to. But I'm going to do that just to make it look a little bit simpler. So I have delta T is equal to 2 delta S over A in a square root sign. Okay, so all I'm doing is I'm rearranging to solve for delta T. If you'd rather substitute your numbers in first, that's fine too. And then I'm going to plug in my numbers. So I have 2, my delta S we said was 73.4. My acceleration was 9.81 sine 10. And then it's all in a square root sign. Somebody want to type that up and let me know what you get? Oh yeah, I already see an answer. I'll type it too. Yeah, I'm getting 9.28. Yeah. So try typing that in. Don't forget that you have to square root it. So I get 9.28 meters. There's 3 significant figures here because my question has 3 significant figures. And typing the answer in all at once after you've rearranged is ideal because then you won't have rounding errors. So if you were to type stuff up at the beginning and then type things up again over and over, you'll probably end up with rounding errors if you don't keep enough digits. So it's always better to do it, to rearrange first and then sub in your numbers. And yes, thank you. The time, if this is time, this isn't distance. So the units would be seconds. Thanks. You are all on the ball. It's good. Mohammed, do you have a question?
Yeah, so I'm wondering, if this was on the test, would we have to write plus minus at the top and then at the bottom for the final answer we wouldn't write plus minus because
you don't have to write it. So basically it's good. What you're saying is really good. So it's good to think about when you do square root something, you would plus and minus it. But because this is time, you can't have negative time. So then you could say, okay, I don't have to put that in. It's good to think about it, to always have that come to mind whenever you're getting rid of a squared by square rooting both sides. You should always say, okay, it should be plus or minus the square root. But then you would say, well, wait, this is time. I don't need to put a negative in front of time because there's no such thing as negative time. Okay, that's a great question. You wouldn't lose marks for not putting it in.
Okay.
Does anybody else have a question?
Okay, thank you.
Okay, so that was question 3. Okay, question 4. A car traveling 30 meters per second runs out of gas while traveling up a 10-degree slope. How far up will he reach, or will it reach? 10 degrees. Starts off over here. We want to know where does it end up. Okay. So what information do we know here? The initial is 30 meters per second. Good. What else do we know? Okay, can we say acceleration is 9.81? Acceleration points this way, straight down, right? If the object is moving up or down, we can use acceleration as 9.81. If the object is moving on a ramp or on an incline, we need to find the component of acceleration that is parallel to the direction that the object is moving, so parallel to the incline. So this is 9.81. This is our theta. This is the acceleration we need to use. And remember we said it was opposite sides, so we're using sine. And that angle theta is the same as this angle theta. Okay? So that's what we're putting in for acceleration is 9.81 sine theta. Now we need to decide whether it's positive or negative. So the object, the car, is moving up the ramp. So let's say up the ramp is the positive direction. And so then that means that its initial velocity is positive because this car is moving up the ramp, so velocity would be positive then. But what should the acceleration be? Should it be positive or negative? Yeah, good, negative. Notice my vector here. Acceleration pulls things down. So if it's a ramp, it would be pulling it down the ramp. So it's negative. Okay, V final is 0. That's great. So the object, the car starts here. It gets to some maximum height along the ramp, and then it comes to a stop. So it says, how far up the hill will it reach? So that means it stopped moving, because if it's still moving, it's still going to be going further up the hill. So this is where it reaches. So this is the maximum distance it travels. And so at that point, its velocity is 0. What is it that we're looking to solve for? Yeah, good. So delta S, it's not time. The question says, how far up the hill will it reach? It doesn't say how long does it take to reach that position. Okay, so how far up the hill? So we could say, okay, we're looking for this, which is delta S. The other way we could do it is we could say our initial position is 0, and we're looking for our final position. So it doesn't matter which way we do it. Okay, I'm going to say delta S is my question mark. Okay. So this time we know V initial, we know V final, we know acceleration. We're looking for delta S. What's the one variable we don't know and that we don't need to know? Yeah, good. Delta T. I'm just going to do this every time just to help you to think about which equation we should use. So because delta T is the one variable we don't know and we don't need to know, we're going to use the equation in the kinematic equation that doesn't have delta T in it. So that's this one, V final squared equals V initial squared plus 2A delta S. Right? So we're solving for delta S. So I prefer to rearrange now if we can. So that means we're going to bring the V initial squared to the other side. V final squared minus, because when you move it over to the other side of the equals, it changes its sign, equals 2A delta S. Now we want to get rid of the 2A because we're solving for delta S. So we want that 2A gone. But 2A is being multiplied by delta S. So to get rid of it, we want to divide both sides by 2A. So we get delta S is equal to V final squared minus V initial squared over 2A. V final we said is 0 minus V initial, which is 30, over 2, and the A is negative 9.81. I didn't put the actual angle in here. I should have. The angle was 10 degrees. Sine 10. And then we can just type that up. Make sure your calculator is in degree mode. And I'm getting 264 And I'm looking at significant figures, so there are 3 here, and there are 3 here, and my acceleration has 3, the 9.81, so I'm going to leave it as 264 meters. Okay, so V final is 0 in this question, Sonia, because the car starts off at the bottom of the ramp and it says, how far up the hill will it reach? So the question is really saying, like, how far will it get to? How high up the hill will it get to before it comes to a stop? So that's why V final is 0. So if something is going up a hill and it says, how far is it going to go? It implies how far does it go before coming to a stop? Because if it hasn't come to a stop yet, then it's still going up higher and higher. So V final is 0 for that one. Does that make sense, Sonia? Okay, I'm going to take a look at question 2 quickly again. So in question 2, a stone drops and hits the bottom of the well. So this object, this stone, when it hits the bottom, the velocity, final velocity is not 0. The velocity is getting faster and faster. So as the object is dropped into the well, it starts off with initial velocity of 0. We say up is positive, so I'm going to stick with down being negative then for this question. The initial velocity is 0 because it got dropped, and now the velocity is getting more and more negative. So it's, let's say it's -1 meters per second, and then it's -2 meters per second. And then it just keeps getting faster and faster until it eventually hits the ground. While it's hitting the ground, it's going fast, right? It's different from somebody who's in their car and driving. Let's say you're driving 100 kilometers per hour, and then you see a stop sign over here, okay? And then you put your foot on the brake. So you're driving 100 kilometers per hour, you put your foot on the brake, and you start driving slower and slower and slower and slower and slower and slower until you stop. And here your velocity is 0. You see the difference between the two? In the example of the stone dropped into the well, it's going faster and faster and faster, more and more negative velocity until it hits the ground. And as it's hitting the ground, its velocity is super fast. Okay, good. I'm glad it makes sense. Okay. There was another question about explaining horizontal component of acceleration. Okay, and that's really the most important thing about this part, this topic that we're doing right now, is that the acceleration itself is not 9.81 anymore, because even though gravity is the force that's acting on the object, making the object go up or down the ramp, or slowing it down or speeding it up as it's moving, the direction that the acceleration is pointed when you're using it in a kinematic equation needs to be in the same direction as the object is moving. So either the same or opposite direction, but on the same axis. So you can't have an acceleration that points downwards and a velocity that's pointing up the ramp like this and use both of those numbers in a kinematic equation. It doesn't work. You need both of those vectors to point in the same direction or opposite direction. So on the same axis. So we're using this axis here. This is our x-axis, and this is our y-axis. And so this acceleration that we have here, which was 9.81, we need to find the component of it that's in the same axis as the direction of the velocity. So that would be this component here. So when we take that vector, and this angle here is theta, which is the same as this angle here, this vector down here would just equal 9.81 sine theta. And that's the number we use in the kinematic equation whenever we have an object traveling on a ramp. Okay, and because we said up the ramp is positive, that's why we needed to put a negative in there. I hope that's clear. Okay, so Ali, do you want to speak your question out loud? Because just to let me know which part of this question you want me to re-explain. Okay, so I'm not sure if it's more clear now, but basically we went through the question, we put in all the variables we know. The one thing that's different from every other question that we've done in previous sections and in the previous lecture was that our acceleration now is not just negative 9.81, it's negative 9.81 sine theta because this object is moving along the ramp. So now we're just plugging in all the variables into the kinematic equation after we rearrange to solve for what we're looking for, which was the delta S. And when we do that, we get 264. Good, I'm glad you understand. Awesome. Okay, any questions about this one before we move on? Remember that if you have to head out while we're still going on through this lecture, I don't want to speed things too much. I'd rather just go slowly and answer everybody's questions. And then that way, if you have to head out, you just watch the rest of the video, whatever portion you haven't seen. Cos theta. You're going to be using cos theta later when we start talking about forces and the normal force. But for now, you don't need to use cos theta in this lecture at all. Okay. For question 3, why did we multiply delta S by 2? So we were here in question 3. So I'm going to do that on the side, sorry. Delta T squared equals delta S divided by 1/2 A. You can just leave it like that, but all that I did was I changed that to be 2 delta S over A. Those are equivalent to each other. Okay, so you could leave it as 1/2 on the bottom, or you can put the 2 on the top. It's the same thing. Okay. Hopefully that's clear. Dafari, do you have a question?
Yeah, for question number 4.
Yeah.
I know why we got sine theta for the gravity, like the acceleration, because like it's on an angle. But yeah. I was just wondering if you could explain like that little diagram you drew.
Yeah.
Or like.
Yep.
Yeah.
It's really important you understand it because I don't want people just like memorizing that it's sine theta. I want you to actually understand it, right? Well, let me just do it again right here. So if this is 10 degrees, and this is gravity that goes straight down, which is 9.81, and you want to decompose that into the 2 vectors, one that's perpendicular to the ramp and one that's parallel to the ramp. So what we're trying to find is this AX over here, right? The one that's parallel to the ramp, because that's the one that's going in the same direction as the velocity. Well, to know what that equals, we need to figure out where does that 10-degree angle belong in this triangle. We know that this angle is 90 degrees because one of those vectors is perpendicular to the ramp, the other one's parallel, so then the 2 of them have to be perpendicular to each other. And if we were to draw this here as a triangle, if that's 10 degrees, this is 90 degrees, then this has to be 80 degrees over here, right? Do you see that?
Yeah.
And so if that's 80, then this has to be 10. And now since it's 10 degrees, then this is the opposite side, AX, so we use sine. So it would be 9.81 sine 10 degrees.
Okay.
Okay. Yeah. Good. Mohammed, do you have a question?
Yeah, for question 3, do we have to show our work when we put like 2 times delta S?
You can do it like this.
Divided by A. Sorry?
You could do it like this. You could write delta T squared equals delta S over 1/2 A, and then plug your numbers in like that. 73.4 over 1/2 times 9.81 sine 10. Is this what you mean?
Yeah, no, but if you like you did another way where you put 2 delta S divided by acceleration.
Yeah.
Would we have to show our work on how we got there?
Well, you have to show your work because if you don't and you don't get the right answer, you're going to end up not getting any part marks. So you want to make sure you're showing your work. So you want to show like the equation you're using, and then you want to show that you're plugging in the correct numbers and that your answer is right. But if you don't do any of that, then you're going to like not get any of the marks for all the work you did like on the side in your calculator. You might as well write it down.
Okay, awesome.
Okay.
All right, thank you.
No problem. Okay, does anybody else have any questions before we move on to the next question? Mohammed?
So similar to what someone else recently asked.
Yeah.
Okay, so I could be wrong, but in an earlier question, I think it was the question before this, when you were getting sine and then the angle,
Yeah.
I think you only used one triangle, right? Or did you use two?
Is it this one?
Yeah, so you used two up there?
Well, really, the only thing I did with this triangle on the left, this one here, is I'm trying to show you why this theta over here is the same as this theta here. That's it. I don't use the other triangle at all, other than to know that this angle here is the angle of incline of the ramp.
Okay.
So once you have that, you're just using the one triangle over here, right?
Yes.
The one with the red and green.
Yeah.
To figure out what the acceleration is that's in the direction parallel to the ramp. So that's this AX down here. So this is the important thing that we just learned today, is to find the acceleration that's parallel to the ramp. You do 9.81 sine of the angle. And I want you to understand why it's like that. I don't want you to just, listen to me tell you that that's the equation and then just memorize it. I want you to just understand that that's why it's 9.81 sine of theta, because this angle over here is the same angle as the angle of incline of the ramp. And then this side over here is opposite of that. And so that's why we're using sine.
I see. I get all of that. The only thing I don't understand is the two green lines. Okay. So like, how would I know to draw it that way? You said something about looking what's perpendicular and what's...
Yeah. So if you have an acceleration that goes straight down and you want to decompose it into something that's parallel and perpendicular to the ramp, you're going to draw two lines on this triangle, like to make a triangle with this vector. One line is perpendicular with the ramp, like this. The other one's parallel to the ramp, so it's like this. So one vector goes like that. The other one.
How do we know to do that, and why?
Because you're decomposing. When you decompose a vector, it means that you're always drawing a triangle where the two sides of the triangle you draw are perpendicular to each other.
Oh, that's right.
And because you're trying to find the acceleration that's parallel to the ramp, that's what that means. You're finding this vector right here.
Oh, so you mean?
Oh,
I think I get it. So
okay, it's on angle, so it's a little confusing.
The long line that's diagonal, that's the ramp. Okay.
Yeah,
and then we draw a line parallel to it, so it's just like straight. I get that. And then one goes directly down because it's gravity, and then you just fill in. Okay.
This is AX.
Okay.
Okay. Remember I told you at the very beginning I did it wrong. I drew it like this, and I drew it like something like this. Right? And I said that's wrong because this vector here is not parallel to the ramp. And a lot of people do it like that. But what's important is the vector you started off with, it has to be the hypotenuse. So the way I just drew it is not right. It's not the hypotenuse. I have to draw it like this.
I get it.
This is parallel to the ramp. This is my AX. Okay, I know it's confusing when you first start doing it.
Yeah, thank you. I get it.
Okay, good.
And
any other questions?
Like the angle between the original slope and the first line you drew, not like AY, that's a 90-degree angle always, right?
Sorry, let me just make sure I understand.
Yeah, what's the logic behind that theta equaling that theta? I know you said it, but...
It's okay, yes. This is A, this is AX. Sorry, first I'm just going to answer Jafari's question. What were you saying about the 90? Is it this one?
Yeah, so it's a 90-degree angle between like AY and like the original slope of like the ramp we're looking at, right?
Yeah, because the definition of AY is that it's perpendicular to the ramp.
Okay.
Okay, and AX is, the definition is that it's parallel to the ramp. So those two have to be perpendicular to each other, right? If you have one thing that's perpendicular to the ramp or one that's parallel, they have to be perpendicular.
Okay, I'm sorry.
Okay. Sonia, do you have a question?
Yeah, could I clarify something
Yes.
about question 4 again, please?
Yes.
Okay, so for a question like this, we just assume that the car slows down.
Yeah, because it says a car is traveling 30 meters per second and it runs out of gas. So it's going to come to a stop eventually because it's going up a hill.
Yes.
And it says how far up the hill will it reach? So it's saying like how far will it go before it comes to a stop?
So it couldn't be like just an abrupt stop, like we don't.
No, because it ran out of gas and it's just coasting up the hill. So it doesn't mention like nobody's pressing the brakes or anything. It's just the fact that there's no gas driving it forward. Now it's just coasting up the ramp.
Oh, okay.
It's eventually going to come to a stop.
Okay, it runs out of gas while it's traveling.
Yeah.
It's coasting. Okay, that
Yeah.
makes sense. Okay, thank you.
Yep, no problem. Okay, next question. Question 5. If an object is not moving at a constant acceleration, then you can't use the kinematic, oh, it's really small, sorry. You can't use a kinematic equation for the one problem from beginning to end because the kinematic problem assumes that acceleration is constant. Okay? Oh, was I supposed to explain something? The thetas equaling each other? Do you want me to explain that again, Mohammed?
Yeah, but if you're recording, you could just do it after. I'll stay the class.
You know what? I explained it probably 3 times, so we could just stay. You could stay with me at the end, and I'll do it again with you. Okay?
Yeah, that's fine.
Okay. Everybody else is probably tired of hearing it. All right. So in this question, because the accelerations, no, don't be sorry at all. Because the accelerations keep changing in the question, we need to divide the problem up into parts. So let's read it. It says a test rocket is fired vertically upward from a well. A catapult gives it an initial speed of 80 meters per second at ground level. Its engines then fire and it accelerates upwards at 4 meters per second until it reaches an altitude of 1,000 meters. At that point, its engines fail and the rocket goes into free fall. Okay, so there's different things happening. So initially it has a speed of 80 meters per second, and then it accelerates at 4 meters per second squared until it reaches an altitude of 1,000 meters, and then at that point, its engine fails, and now it's not accelerating due to the engines anymore. It's now just under free fall, which means it's just gravity. Oh yeah, thank you. Thanks, Marion, for your comment. It's true. I understand that some things are confusing and people ask questions, and I try to be mindful of your time, but at the same time, I want to make sure you all understand everything. So please don't hesitate to ask questions. If the same question keeps getting asked over and over, it's because I'm not clear, or because maybe it's just really confusing and you need to hear it over and over, and that's totally fine. Okay. So do people want me to go over the angle question again, or should I just leave that? Everybody's in a different position, so don't worry if this is new to you or if it's not. So I think we'll move on with this question, and then I'll go. The angle question is not going to come back during this lecture until like at the end we'll go over that again. Okay. All right. So let's draw a picture of what this looks like. So we have a test rocket fired vertically upward from a well. A catapult gives it an initial speed of 80 meters per second. Okay, let's draw this. So this velocity is going to be 80 meters per second at ground level. So it's at the bottom here, okay? So I'm going to say that this is S1 and its initial position is 0 meters. Its engines fire and it accelerates upwards at 4 meters per second until it reaches an altitude of 1,000 meters. So it goes up like this. It gets to 1,000 meters. This is my Y, or I can call it S. And then once it gets to 1,000 meters, what happens? Its engines fail and the rocket goes into free fall. So this whole period here, oops. Oh, I don't know what to do with the pen battery. I think it just needs to get charged. Okay. The acceleration here is 4 meters per second squared. And then at this point, it says the engine fails and it goes into free fall. So at that point, what is the acceleration once the engines fail? Good, 9.81. We're going to say up is positive in this question. So it's going to be negative 9.81. Now, is there a ramp here? Do I have to do sine theta or no? No, there's no ramp in the question. Good. So now what's happening is the engine does not work anymore. It's failed. And now our acceleration is negative 9.81 meters per second squared. Now, as soon as the engine fails, is this rocket going to instantly just crash and come to the ground? Or is it going to keep going up a bit and then come down? what's going to happen? Is it going to keep going up, or is it going to just suddenly go down? Yeah, because it's on its way up.
And go down.
Yeah, it's on its way up and it's moving quite fast. And now it's still moving upwards. It's going to keep going up, but it's getting slower and slower and slower until eventually it comes back down and then it hits the ground. Okay, so it goes up a bit and then it goes back down. And during this whole period from here to here, the whole way, the acceleration is now just due to gravity, 9.81 meters per second squared down. Whereas the beginning bit, the acceleration was 4 meters per second squared. So because there's two different accelerations, we really need to split this question up into two different parts. And instead of using V1 or V initial, V final, for example, I'm using V1, V2, V3, S1, S2, S3. So this here, I'm treating it like it's my position 1, and this one is my 2. And actually, the question asks us about a maximum altitude, so I'm going to call this position here 3, and down here 4. So I'm not going to use initial final because it gets confusing because we have to split this up into different parts. Okay, so let's write down the things that we know. If we look at just 1 to 2, what I mean by that is this section here from 1 to 2. Okay, I'm just going to focus on this first. Okay, from 1 to 2. So my V1, I said, was 80 meters per second. My acceleration is 4 meters per second squared. My S1 is 0 meters. So what can we find here? What are the pieces of information that we don't know? Oh, and also we know my S2 is over here, is 1,000 meters. Bye, Sonia. Enjoy the ending of the recording. Okay, so we have S1, S2, V1, and A. So what is it that we can figure out here? We can find delta T, and we can find V2. So we're going to do those. We're going to use a kinematic equation to find delta T, and we're also going to find V2. But instead of calling it delta T, we're going to call it T2 because this is going to get too confusing because we're going to have delta T's all over the place. Okay, so I'm going to call it T2. And we're going to say T1 down here was initial when it was 0. The initial time at the beginning is 0. So let's try solving for something. So let's start with T2. So in this case, we're going to ignore V2. We don't need it yet, and we don't know it. So we're going to use the equation that doesn't require it. So we're going to use S2 equals S1 plus V1 delta T. And instead of delta T, I'm going to rename that T2 minus T1 plus 1/2 A Okay, so delta T, delta means change in, so it just means T final minus T initial, and I'm using 1s and 2s instead. So my T1 is just 0. So let's start plugging in everything we know. I'm just going to cross off things that are 0. So we can solve for this T2, but we'd have to use the quadratic formula. So I'm just going to simplify it a bit. Okay, so I got T2 is 10. Any questions about that so far? I just used the quadratic formula and I typed it all on my calculator. So that's T2, and then we're also going to find V2 because we're going to need to know what this time is here and what this velocity is here so we can figure out what the time and velocity is at 3 and at 4. That's why we're doing this. So let's look for V2. So we can use a different kinematic equation. We can say V2 oh no, I'm having a tech issue. My pen stopped working. 1 second. Oh, this is going to be horrible to do with a mouse. Let's check. Okay, it's working. I charged it for a second. Okay, so I'm solving for V2 now. So V2 equals V1 plus A delta T. So my V2 is what I'm looking for. My V1 is 80. My A is 4. And my time is 10. So delta T is the same. I'll just rewrite it so it's a little bit more clear. Is T2 minus T1. So it's 10 minus 0. So 80 plus 40 is 120. So this whole ones and twos, it seems pretty confusing right now, especially with the times. Normally we just write delta T, but because we're trying to find the time it takes to go from point 1 to point 2, and then to point 3, and then to point 4, instead of writing delta T each time, I'm choosing to use 1, 2, 3, and 4 to make it a little bit more organized. So now we know everything about point 2. So we know that at point 2, the time now is 10 seconds for us to get to point 2. And then the velocity here is 120 meters per second. And we know that the height, or the S, the position at point 2, is 1,000 meters or 1,000 meters. So now we can go from 2 to 3 to figure out information about 3. So from 2 to 3, we know all this stuff about 2. So we know T2, V2, and S2. Now, how do we figure out what 3 is? All the information for 3. Well, we also know that the acceleration is negative 9.81 meters per second squared. So let's try to find out what V3 is. And let's also try to find out what T3 is. Does somebody want to stop me and ask a question? Because I know it's kind of confusing. Yeah, so V3. So Sathujan, you've already kind of said the answer. I'm using numbers rather than initial and final, but yes, V3 is the position when you're at this maximum, the velocity when you're at this maximum height. And when you're at the maximum height, your velocity is 0. So this is 0 meters per second. So we already know that. Okay. Bye, Dafari. Okay, so now let's try to find T3 and also S3. So those are two things that we want to find. So we'll start with T3. So let's think of a kinematic equation that we can use. We can use V3 is equal to V2 plus A T3 minus T2. Okay, it looks pretty confusing. I'm using this equation. V final equals V initial plus A delta T. But we're in section 2 to 3. So final is 3 and initial means 2. And delta T is the same as T3 minus T2. Does that make sense to people? Do you have any questions? Okay. Let me know if you have questions, because I know it's a bit confusing with all these numbers. So we're looking for this T3 over here. Okay, so V3 is 0. V2, we already know from before, was 120. Notice how we needed to figure out what that was before we could do this question. So this is why. That's why we solved for it before. Plus A. Now our A is negative 9.81. T3 is what we're looking for, minus T2, which was 10. So when we solve for T3, we're not just finding the time it takes to get from 2 to 3. We're finding the total time at 3. So T1 was 0 seconds. 10 seconds go by and we're at 2. Now, when we solve for T3, that's the total amount of time, considering T1 was 0. How much time does it take to get to 3? That's the total. Okay, so let's solve for this T3. So we have 120, and now I can multiply this in. Actually, I'm going to rearrange it differently. So I'll bring the 120 to the other side, equals negative 9.81 T3 minus 10. And then we can divide both sides by negative 9.81. So we get negative 120 divided by negative 9.81 equals T3 minus 10. And then we'll add 10 to both sides to get T3. The two negatives cancel out. And I'll just type this up. .23 seconds. Okay, so now this is the amount of time it takes to get from the beginning to T3. So that's how long it took to get to the maximum height. So now we can move on to 3 to 4. And that's the last bit here. From 3 to 4. So at 3, now we know what the time is. At 3, it was 22.23 seconds. We know what the velocity was 0. And we still know that the acceleration all the way from 3 to 4 is still the same number. It's the negative 9.81 meters per second squared. It's still in free fall. Okay. So we have V3 is 0. T3 is 22.23 seconds. Oh, we never found out what the S3 was, so we should go back to that. S3. We should figure out what S3 is because question B, part B, says what is the maximum altitude? So that's really what is S3? What is that? So that's what we need to solve for still. So if we're going to solve for S3, the equation would be S3 equals S2 plus V2 delta T, which is T3 minus T2, plus 1/2 A delta T squared. I'll write it on the side. S final equals S initial plus V initial delta T plus 1/2 A delta T squared. Notice we're in 2 to 3, so that means final is 3 and initial is 2. And delta T means T3 minus T2. And same with this one. So delta always means the change. So delta T means the final time minus the initial time. So that's why it's always a minus and not a plus. Okay. Why is T 3.1 to 3 and not 2 to 3? So T3, so when we do this, what we're doing is we're already finding out the total amount of time. So basically, like, what time is it now? So initially, the time was 0. At 2, the time is 10 seconds. At 3, the time is 22.23 seconds. It's the total time. It's what the time reads on this axis, 22.23. This time over here is 10. It's what the time is reading on the axis. It's not finding the change in time between them because we already did That's why in our equation we're doing T2 minus T1 or T3 minus T2. We're actually finding this number on the scale, on the axis itself. Okay, Mohammed, do you want to ask a question?
Yeah, I understand everything so far, but I just don't understand where you, for T2, how you did the division. I mean, how you solved that to get 10 seconds.
Oh, at the very beginning? Over here? Is that what you mean?
Yeah, that part.
I used quadratic formula. I did it on my calculator without showing any work. Does that make sense?
Yeah.
So I did that and I solved for T2. You probably could have also just factored and it would have worked too, since the number was a nice even number.
Okay, thank you.
Yep, no problem. Yes, and Sajuthan, you can do, sorry, Sathujan, you could do the same thing. What you were saying is you can find delta t's for each section and then add them to the previous time to find the total time. Yep, that's fine too. Okay, no problem. Okay, so let's start finding this S3. So S2 is, let's see, we wrote it down, it's 1,000 plus V2, which was 120. T3 is what we're looking for, minus T2, which is 10. It's this, minusing the 10 is what's making us find the total, because when we solve for T3, we're bringing that minus 10 to the other side of the equals later, and it becomes adding 10. So that's why we're already adding it to it. But if you wanted to just find delta t for each of these and then add all the delta t's, that's good too. 1/2 a is negative 9.81. T3 is what we're looking for, minus T2, which is 10 squared. And S3 is what we want. Oh, sorry, so I should have put in my T3. We found T3 already. It was 22.23. So that's what goes here. And then we can type all of this up. So I'm going to type this up. Okay, so I'm getting this number. I don't know if anybody else tried typing it. You can confirm it. It's 1733.94 meters. So that's S3. So now finally we're in this last section over here. And so we have our acceleration, our V3, our T3. The question for part C is saying what is its velocity when it collides with the Earth? So that means it's asking for V4. But part A also asks how long is it in motion? So that means what is T4? So what is this time over here when it hits the ground? Okay, so that number we need to find as well. I'm going to get rid of that 4. Okay, so V4 and T4 is what we want. And we know what S3 is, which we just found below, 1733.94. And we even know what S4 is because it hit the ground, so it's 0 meters. So now we can use all that information to figure out what V4 is. So, and what T4 is. So let's see. So let's do delta S, or S final, S4 equals S initial, which is S3, plus V initial, which is V3, delta T, which is T4 minus T3, plus 1/2 A delta T, which is T4 minus T3 squared. So we're solving for T4 first. So my S4 is 0. My S3 is 1733.94 plus V3 is 0. So let's just right away, since this is 0, this whole thing is gone. 1/2 A, which is negative 9.81, T4, which is what we're looking for, minus T3, 22.23 squared. Okay, so now we have to solve for this T4 over here. So we can bring things to the other side. So we have negative 1733.94 equals 1/2 times negative 9.81 times T4 minus 22.23 squared. Now we can divide both sides by 1/2 times negative 9.81. So we have T4 minus 22.23 squared equals negative 1733.94 over 1/2 times negative 9.81. Now we need to get rid of the squared, so we have to square root both sides. So we have T4 minus 22.23 equals the square root. We can do plus or minus square root, but again, we don't want to have a negative time, so we don't really need to worry about the minus part. And the negative here and the negative here would cancel out. Okay? So it's fine that you're going to end up having a positive value in your square root sign. 1733.94 over 1/2 times 9.81. And then finally, we just have to bring that 22.23 to the other side. T4 is equal to the square root of 1733.94 over 1/2 times 9.81 plus 22.23. This is that plus adding them. That means you're finding the actual time at that point, not the delta t. So that's what I was talking about since you're doing that adding the 22.23. I'm going to type in the numbers. And I get 41.03 seconds. And I also need to find V4. This is a huge question. So V4. So now I have V4 equals V3 plus A delta T. And delta T would be T4 minus T3. Okay, so it's like saying V final equals V initial plus A delta T, but final is position 4 and initial is position 3. Okay, so V4 is what I'm looking for. V3 we said was 0, so that's just gone. Plus A, which is negative 9.81, T4, which is 41.03, minus T3, which is 22.23. And there's that delta T again, right? Because we subtracted the 22.23 now. So negative 9.81 times 41.03 minus 22.23. And I get negative 184.4 meters per second. Okay. Good. I just noticed your comment, Marian. Perfect. You got the right answer for the time. And so now for V4, I'm getting negative 184.4 meters per second. It makes sense that it's negative because we said up is positive, but the object is hitting the ground and it's going down. So it would be a negative velocity. The only thing left to look at now is our significant figures. So let's go ahead and answer all the questions. How long is the rocket in motion above the ground? So the total amount of time was the 41 seconds. The question gives 3 significant figures, 3 significant figures, and 5 significant figures. So our answer should have 3. So it would be 41.0. Okay, so this question just has some rounding errors. So it would be 41.0 seconds. So that's the answer for part A. For part B, what is the maximum altitude? So that's when we found S3. That's the height right here at 3. So that was this answer here. S3 is 1733.94. We want 3 significant figures, so that would be about 1730 meters. Again, on your test, you'll be asked to round to 2 decimal places unless it specifically tells you otherwise. Then you would put decimals in here. Okay, so that's part B. And then for part C, what is the velocity just before it collides with the Earth? It's the negative 184. We just need to round it so it only has 3 significant figures, meters per second. So that's our V4. And that's part C. Does anybody have any questions about this super long question? I know it was very, very long.
Will there be a question like this on Wednesday's test?
It won't be this. It won't be a question like this. No, it wouldn't be this long because you only get an hour, right, to do the whole thing.
Yeah. Okay.
Yeah. I hope you found the first test to be fair. My intention is not to try to trick people or make it unfair. Okay? Okay, let's move on to the next question. Okay, so now we have objects catching up to another. We have, there are some more questions here, 6, 7, 8, and 9, I believe. Yeah, so 6, 7, 8, and 9. Now 7, 8, and 9, I have video solutions that are in the homework questions, so I'll just have you watch those on your own later. So I'm going to do one example together so you can ask for help, but they're all very similar to each other. I just wanted to give you more practice questions to do. So let's do question 6 together. So what's happening in question 6 is we have an object catching up to another object. Let me make it bigger so you can see. Okay, when an object catches up to another, that means that they're both at the same place at the same time because one object caught up to the other one. So that means that the final position, SF, and the final time are equal to each other. So if you're going to solve problems like this, and you will see a question like this on your test, you have to state all the known values for each object. So you have 2 objects, one is catching up to the other. Bye, Mohammed. Thank you. Have a good day. Okay, so we're going to have a table that separates the 2 objects from each other. So we have a child riding her bike at a constant speed, and just as she passes her dad begins to run to catch up to her. So we're going to divide this up into, like, using a table. We have a child and we have a dad, and we're going to put all the kinematic information in this table. So we have our initial velocity, final velocity, acceleration, our initial position, our final position, and our delta t. Okay, those are all the variables in the kinematic equation. So what do we know about this question? The child has a constant speed of 3.5 meters per second. So that's her constant speed. It's her initial speed. It's her final speed. It's a constant speed. And if her speed is constant, then what is her acceleration? Yeah, good. Acceleration is 0. Good. Her dad, who is standing at rest, meaning that his initial velocity is 0, begins to run to catch up to her. His acceleration is 1.5 meters per second squared. How long does it take for the dad to catch up to her? Okay, so their initial position, it doesn't mention anything about it, but they both started from the same spot because it says just as she passes her dad starts running to catch up to her. So they're both at the same position. So let's just say their same position is 0 then, to make things simpler. So they're starting off at the same position. Let's say this is 0. And she's moving along at a constant speed, and he's stopped. Originally, he doesn't have a speed, but he catches up to her. So he gets faster and faster because he's accelerating. So how long does it take? Well, if he catches up to her, then that means that they have the same final position at the same time. So I'm putting equal signs here to show that those positions and those times are the same. So if we look at a kinematic equation, SF, the same position for the dad would equal the final position for the child. Final position of the dad equals final position of the child, because that's what it means when somebody catches up to someone else, right? They're at the same position at the same time. So from a kinematic equation, we can say SF equals SI plus VI delta T plus 1/2 A delta T squared. So for the dad, that would be SI for the dad plus VI for the dad delta T plus 1/2 A for the dad delta T squared. Same thing for the child. SI child plus VI child delta t plus 1/2 A child delta t squared. And so really now, because we made the final positions the same, the only unknown value is delta t, but we already said the delta t for the dad is the same as the delta t for the child. So we can plug in everything we know and just solve for the delta t. I'm going to start by just figuring out what's 0 so I could cross them all off. The child's acceleration is 0. So I'm going to make the acceleration term for the child be 0, which means this whole term goes away. The dad's initial velocity is 0, which means this initial velocity for the dad is 0, and this whole term goes away. What else? The S initial for both of them are 0, so these two are just gone. So now our equation is a lot more simple looking. So let's start to, I'm going to rewrite it, and then I'm going to start to plug in. Okay, so let's plug in what we know. 1/2 the acceleration for the dad is 1.5 delta t squared plus the v initial for the child is 3.5 delta t. And now we're just solving for this delta t. So I'm going to multiply 1/2 times 1.5 is 0.75 delta t squared. And I'll bring the 3.5 to the other side. Oh, I forgot my equal sign up above. That's an equals. So I'm going to bring the 3.5 delta t to the other side equals 0. I could factor out a delta t, and I'm left with 0.75 delta t minus 3.5 equals 0. And now I can solve for delta t. Delta t equals 0, and 0.75 delta t minus 3.5 equals 0. And then I can solve for my delta t here. So it equals 3.5 divided by 0.75. Is 4.66. Okay, so question A, part A says, how long does it take for the dad to catch up to the child? The answer is 4.67 seconds. Any questions there? And then we can keep going to answer part B. So part B says, how fast is the dad running when he catches up to the child? So we're just looking for the V final for the dad. Okay, so we know the V initial for the dad is 0. We know the acceleration for the dad is 1.5. And we know that the time is 4.6667 seconds. So notice I'm just putting in more digits here so that our answer is more accurate. So I'm looking for V final. So it would be V final equals V initial plus A delta T. My V initial is 0, so that's gone. My A is 1.5, and my delta T is 4.66667. And I get 7. Exactly 7 meters per second. Okay, and then the final question is, what's the total distance the dad ran? So I'm going to do that right here. So that's just my delta S for the dad. Equals V initial delta t plus 1/2 A delta t squared. Again, our V initial for the dad was 0. So we have 1/2. The A was 1.5, and the delta t was the 4.66667 squared. And I'm getting about 16.3 meters. Let me just zoom out a bit so you can see the whole thing. There. Okay, so the key with these questions is you want to organize all your information separately for the two different objects or the two different people in the question. And then once you've organized it with this table, then you can start to look for what the question's asking for. So you're going to solve for delta S or S final for both objects and make those equations equal to each other. See, the SF for the dad is equal to the SF for the child. And since the delta t's are equal, then you can now solve for delta t, and then you can move on and answer all the rest of the questions. Okay, so questions 7, 8, and 9 are very similar to this. I just wanted to give you more practice, and there's a video solution already posted in the homework section.